All right, now we are going to graph all different types of rational functions. So everything is up for grabs in this situation. So what we have been graphing is like just 1 over x and all the different versions of 1 over x. But now we take off the training wheels, kick them to the side, and we just go freewheeling. 1 over x is your basic rational function, right? It's the inverse function. It's the x to the -1. It's x times y is equal to k, right? Or x times y is equal to 1. It's your basic function. But now we can just do all kinds of crazy things. Before we graph one of these, we're going to talk about general features of any function that you want to talk about and graph. Important features of any graph, the y-intercept. Well, how do you get the y-intercept? Well, you make x 0. You set x equal to 0 in the problem. If you want the y-intercept, you make y equal to 0, or the output of the function equal to 0. And in terms of a rational function, you set the numerator equal to 0. So we set the numerator equal to 0. Set the numerator equal to 0. That will do it. All right. So x equals 0 creates the y-intercept. Y equals 0 creates the x-intercept, and we just set the numerator equal to 0, or the top of the fraction equal to 0. Relative mins and maxes are the places where the function turns. Those are always important to find. And right now we kind of use technology to help us find those. And the vertical asymptote is setting the denominator equal to 0. So we set the denominator equal to 0. All right. Now the horizontal asymptotes are created when x becomes a large number. And there's 3 different scenarios. Okay, so horizontal asymptotes are created when x becomes a large number. So what does this mean? If you have x plus 2 over x squared minus 3, and this is your function right here, and you're putting in huge numbers like a billion. Well, a billion plus 2 is basically a billion, and a billion squared minus 3 is basically a billion squared. So what happens is this, when you put in super large numbers, this behaves like x over x squared, and x over x squared is really 1 over x. So for large numbers, this behaves like 1 over x. Well, if you take 1 and you divide it up by a huge number, you're basically getting 0. So anytime you have a smaller exponent on the top of the fraction, a larger exponent on the bottom of the fraction, then y is equal to 0 is your horizontal asymptote. So it's smaller over larger. Now if we switch it and we have y is equal to x squared minus 3 over x plus 2, then the same idea is happening here, but this behaves like x squared over x, because if you put a billion in here, subtracting 3, adding 2, it doesn't really make that much difference. So x squared over x really behaves like just x. So my function just keeps growing and growing and growing. It never really settles and stops. So y would be none, like as in there aren't any horizontal asymptotes. So there's 3 situations here. There's A situation, B situation. So smaller over larger is always 0, large over smaller is always none. Now the third scenario is if there's a tie. So if we have y is equal to 3x squared minus 8 over 2x squared plus 4x minus 7. Okay, well, when we're talking about putting billions in here, then this doesn't matter, this doesn't really matter, that doesn't matter. The only thing that matters is the leading terms. And this is going to behave like y is equal to 3x squared over 2x squared. But then these two would like cancel out, and you're just left with the coefficients in the front. So this would be y is equal to 3 over 2. So this is C scenario. So if there's a tie, you just use the coefficients in the front. All right. So that's really kind of a weird thing that you have to get used to. So what the vertical asymptote happens when you set the denominator equal to 0, and so we have to work on that, but it's also, there could be a hole in the function too. So this gets really kind of confusing and convoluted, so here we go. So example 1, there's a hole in my function. Basically, anytime you have the same thing divided by the same thing, it creates a 1, but you have to include that in the original function so it can create holes in the function instead of being a vertical asymptote. So what I'm talking about here is if we have any function that we want to in the world, like just take a standard parabola, x squared minus 3x plus 8. Okay, that's a standard parabola. And I can multiply the parabola by like x minus 2, and then I can divide the parabola by x minus 2. Now, when I set the denominator equal to 0, I'm not really finding a vertical asymptote. I'm finding really just where the hole is, because the same thing divided by the same thing is 1. So it didn't put a vertical asymptote at 2, it put a hole at 2. So at x equals 2, there's a hole in the function. Now a hole is called a removable discontinuity. Discontinuity. So it's called a removable discontinuity because you can fill the hole with a point and remove the discontinuity, whereas a vertical asymptote, you can't put a point in there to remove the discontinuity. You can't put anything in there to remove it, so it's non-removable discontinuity. But there's a hole in the function. So let's see the hole here. I'm going to get my graphing calculator out. And you could put hundreds of holes in functions. You could put holes in them all day long. So I'm going to go to y equals, clear this out, type in parentheses x squared, x squared minus 3x plus 8. Okay, times x minus 2, and then we're going to divide it by x minus 2. Oops, I need to put that in parentheses. Enter, and graph. So we should see a parabola show up on the screen here. If we don't, then I need to change the window so I can see it. There's my parabola. Okay, I want to look a little bit higher so I can see the parabola better. So if I go to the window, I'm going to turn all, I'm going to negative 10 to 10. That would be okay for right now, and I'm going to go 0 to 15 and see what that gives me. So I'm going to see a little more of the parabola here. Okay, but there's a hole in the parabola at x equals 2. Well, you can't see the hole. So what we need to do is we need to put 2 in the center of the screen. So if I go 2 over 5 spaces, that would be negative 3, and if I go 2 and then 5 spaces, that would be 7. So I'm going to go from negative 3 to 7. That will put 2 right in the center of the screen. So go to the window, and I'm going to do negative 3 to 7. Graph. So 2 is right in the center, and it should put a hole there. Boom. See, there's a little tiny gap in the function. So this isn't a vertical boundary. It's just a hole in the function. It's a discontinuity, but it's called a removable discontinuity because you could put a point in there and fill it. Okay. In fact, we could go to the stats. Let's see, what would that be? If I put 2 here, that would be 4. 12 minus 6 would be 6. So 2, 6 should fill that hole. So I'm going to go to Stat and Edit. And I'm going to put in the point 2 and then 6. So I'm going to remove the discontinuity. 2, 6 is where the hole is, because if I put 2 back in here, I get 4 plus 8 is 12, and then minus 6 would be 6. So 2, 6 is the only hole in the whole thing. I'm going to go to second stat plot. I'm going to turn the plot 2 on, and it's L1 and L2, and it's going to be red. There'll be a red dot there. So then I'm going to change it, not to the box thing, I'll change it to this box right there, and it should fill it in. So hit graph, and then there's the point, and then the parabola is going to come down, and see I filled that hole in with the little red dot. You can't really see the red dot so well. Let me see if I can focus in. So it's you can kind of tell it's a little different color. All right. So in the first slide here, I said setting the denominator equal to 0 creates a vertical asymptote. Well, it doesn't in this case, because you got to look for this situation where there could be a hole in the function. All right. Now we're going to find vertical asymptotes or holes in all these examples here. So the first thing you have to do is factor. So it's x and x minus 4 plus 3. And it's like, do we have the same thing divided by the same thing? No, so there's no holes. So x equals 4 and x equals negative 3 are the vertical asymptotes. And that's it. So if you have the same thing divided by the same thing, it creates a hole. But if it's just dividing by 0, right, you set the bottom equal to 0, that's how you find the vertical asymptotes. Here, we factor, and we can't factor it. And then we try and set it equal to 0, and this doesn't equal 0, right? There's no way to make the denominator equal to 0. So there are none. There are no vertical asymptotes. Down here, we have the same thing divided by the same thing. So that's not a vertical asymptote, that's just a hole. Now where is the hole? Well, it's at the number that makes this 0. So there's a hole. Oops. I'll make that an E. There's a hole at x equals negative 3, because that makes the denominator equal to 0. Down here, and then so these are non-removable, and then that's a removable discontinuity. Here, I've already factored for you, so there's no same thing divided by same thing, so there's no holes, but there's going to be negative 1 and negative 5 make that equal to 0. So x equals negative 1 and negative 5 are your vertical asymptotes, your non-removable discontinuities. Now here, what do I got going on? Oh, I got 2 holes. So I got this, that's 1 hole, that's 2 holes, and then this just behaves like this. Okay, so it behaves like this with a hole in 2 locations. Well, that's going to be kind of weird. So x equals negative 9 and x equals, well, that can't be a hole. And then 6 are the 2 places where there's an issue. So that one has that double thing there. That's really weird. I'd have to graph that and kind of figure out what was going on with that one. That's a crazy example. Okay, now horizontal asymptotes are created by the 3 different scenarios here that I talked about. So is it A, B, or C? Is it smaller over larger, large over smaller, or is it a tie? Well, in this case right here, it's a tie. So we just use the coefficients. So y is equal to negative 4 over 2. Negative 2 is your horizontal asymptote. Okay, now let's graph this bad boy. There are no holes because I do not have the same thing over the same thing. So there's no holes which are removable discontinuities. There's only non-removable discontinuities, or also known as vertical asymptotes. So negative 2 is a bad spot, and 3 is a bad spot because I set the denominator equal to 0, and that causes division of 0 in 2 locations at 3. So I put a line like this. 3. is a boundary, and then negative 2 is the other boundary. Okay, so x equals negative 2 is one vertical asymptote, and x equals 3 is the other one. Now, this is x times x, which is x squared, versus x. So it's a smaller exponent versus a larger exponent. So y equals 0 is your horizontal asymptote. So there's a horizontal boundary here. Okay? So I found the vertical asymptotes by setting the denominator equal to 0. And I thought about the exponents to figure out the horizontal. Set the bottom equal to 0, creates the verticals. Okay, now, if you put 0 into the function, I'm going to start trying points now. If I put 0 into the function, that's going to be the y-intercept. So that would give me 1 on the top, and it gives me 2 times negative 3 on the bottom, so that would be negative 6. So 0, negative 1, 6 is the place where it crosses right there. I'm going to switch over to blue. Let's put my points in blue. Now, I'm going to set the top of the equation equal to 0, the numerator set equal to 0, because that's going to be where the whole fraction's equal to 0. So that would be like making y equal to 0, because that's going to be the x-intercept, and then that would be negative 1. So 0, negative 1, 0 is another point. So, what the question is, what happens at like 2? What's going on at 2? Where is it going to be down here? Where's it going to be? So I'm just trying points to figure out how this thing works. So 2 would be 3 on the top, and it would be 4, be negative 4 on the bottom, because that'd be negative 1 times 4. So 1, 2, negative 3/4, which would be about there. So I believe what happens is this comes down, slithers through like an S shape, like so. And we'll graph it on the calculator to make sure that it does that. All right, now I'm going to try. We need to figure out, does it curve in here? Does it curve over here? So try more points. We're going to do 4, because 4 would be kind of over in this region, because there's 3. So I'm going to try 4. If I put 4 in, I get 5 on the top, and I get 6 on the bottom, because that would be 1. So I get 6 on the bottom. So over 4 and basically up 1. So it's going to curve like so over here. Now I need to figure out, does it curve in here or does it curve up there? So I'm going to put in negative 3, because that would be, there's negative 2, so over to negative 3. That would be negative 2 on the top, and on the bottom it would be negative 6 times negative 6 times negative 1 would be 6, so it would be negative 1/3, which would be right 1, 2, 3 down a little bit, so it's going to curve in here. So there's vertical boundaries and a horizontal boundary, so it has to curve in this region, snake through an S like this, and then like so. Now sometimes these center parts are like a U shape kind of thing, but it just all depends upon the problem. Okay, let's type this in and see if we did it right. Okay, turn the plot off. I don't need that point anymore. Clear this out. So the equation is x parentheses, it's going to be x plus 1 divided by, now I'm going to put in extra parentheses, x plus 2 parentheses, parentheses, x minus 3 parentheses, parentheses. Okay, and zoom standard, zoom 6. Okay, so there it's negative 2, it's where it's breaking. It snakes through. It's also breaking at positive 3, and it snakes through. All right, now if we wanted to add a whole to this function, we would just multiply the numerator and the denominator by the same thing. So you could do like x plus 4 and then x plus 4. If we added that in there, then it'd put a whole at negative 4. So you just multiply the numerator and the denominator by the same thing, and it just makes a whole. So this one here is fairly complicated. What did I do? I set the denominator equal to 0. That found that there was 2 vertical asymptotes. Notice there's no whole because it's not the same thing divided by the same thing. And in order to figure that out, it has to be factored. And it came pre-factored. Then I have a smaller exponent over a larger exponent, so that creates the horizontal boundary. Then basically I just tried points in to figure out how it curves. So if this point is here, it's not going to go above this or to the side of that, so it has to curve in this area. And then the same thing here, I found this point, and then you just kind of have to figure out, does it S through or does it loop through? It all depends, and it changes every time, so that's why it's kind of confusing.